Welcome to AI Paper Slop, the series where we summarize AI and tech papers for ML engineers and AI researchers.
Yep.
Today we are dissecting the Qwen-Audio-VAE technical report by the Qwen team, and here is your 60-second download of the core technical insights.
Let's get right into it.
Yeah, so Qwen-Audio-VAE is a 12.5 hertz continuous audio autoencoder. It's purpose-built as this highly efficient representation backbone for large-scale text-to-audio generation, specifically for training diffusion transformers, or DATs.
Right, which is a huge deal right now.
Exactly.
Yeah.
And the team achieves this massive 1920x compression rate. I mean, this keeps the latent sequences incredibly short, which basically solves that downstream quadratic self-attention cost that usually just chokes DIT models.
Totally. That attention cost is a nightmare.
Yeah. So by combining an asymmetric encoder-decoder architecture with some really aggressive latency-aware pruning, they managed to encode 32 minutes of audio in just 541 milliseconds.
That is just wild.
Right. That's a 3.6x speed up over the standard baselines. And they trained this beast on 5 million hours of curated data. So they're basically proving that you can simultaneously achieve highly compact latents, light and fast encoding, and really high fidelity reconstruction across speech, music, and sound effects.
So I think contextualizing why the Qwen team even built this is really where we need to start. Because if you are building multimodal foundation models right now, the autoencoder is your silent bottleneck.
Yeah, it really is just sitting there dictating everything.
Exactly. It fundamentally dictates the representation that your downstream generator actually has to learn. It sets a hard mathematical upper bound on your final audio quality. And practically speaking, it dictates how many GPUs you are going to burn through during training.
Well, let's frame that bottleneck through the lens of a project management triangle. The classic rule, right? Good, fast, cheap, pick two.
Right. Everyone knows that one.
Yeah, but when you apply that to audio latent spaces, the competing requirements are a bit different. One, you need high fidelity reconstruction across incredibly diverse audio domains.
Which is hard enough on its own.
Totally. Then two, you need a highly compact latent, which means a short sequence length. And three, you need high throughput encoding because you have to have this running online during large-scale training.
Right. You can't have your cluster just waiting around.
Exactly. So the Qwen team is looking at this impossible triangle and, well, they're deciding they just want all three.
Which is ambitious, to say the least, because historically, existing models always fail on at least one side of that triangle. Like, take discrete audio codecs, like DAC or encodec.
Right, those are super popular.
They are, and they use vector quantization, which compresses human speech beautifully. And that's because speech has a very specific predictable structure.
But then you throw music at it.
Right, exactly. The moment you feed those discrete codecs, wideband, high-fidelity music, or just noisy, chaotic sound effects, the quantization error becomes painfully obvious.
Oh, yeah, you get those weird underwater artifacts.
Yeah, because the model is forced to snap these really complex waveforms to a discrete codebook, and you just lose all that rich wideband detail.
Okay, so to avoid that quantization loss, you move to continuous VAEs. Right. Because continuous spaces play much nicer with diffusion and flow-based generators. There are no hard discrete boundaries to snap to.
They definitely do play nicer, yeah. But then that introduces the sequence length problem. Models like, say, Audio or Stable Audio Open, they operate at relatively high frame rates.
Usually between, 20 and 75 hertz.
Exactly, yeah. Usually in that 20 to 75 hertz range.
And I mean, 75 hertz might sound really low to a listener if you were thinking about raw audio sample rates like 44.1 kilohertz.
Yeah.
But we have to remember what this latent representation is actually being fed into, right? It's going into a diffusion transformer.
Right, the DIT. And that's where the math gets scary.
Yeah, because in a standard DIT, the self-attention compute cost scales quadratically with the sequence length. That's big O of L squared.
It just blows up so fast.
Right. So if your continuous autoencoder is pumping out 75 frames for every single second of audio, your latent sequence is incredibly long. The attention matrix just balloons. Your VRAM requirements explode. And efficiently training a large-scale text-to-audio model just becomes computationally impossible.
So to shatter this impossible triangle, the Qwen team really couldn't just tweak an existing architecture. They had to redesign it from the ground up to force this severe bottleneck, but without destroying the acoustic detail.
And they start with a 24 kilohertz input waveform, right?
Right, 24 kilohertz in, and then they compress it by a factor of 1920.
We have to track the math on that because it's wild. So they use a causal convolutional encoder to start.
Yeah.
And that causal padding is actually a really smart choice.
Yeah, it's crucial for deployment later.
Exactly. because it preserves your ability to do streaming and chunkwise inference when you finally ship the thing. So that encoder stack takes the 24 kilohertz waveform and it downsamples it by 480 times. That drops the temporal resolution down to 50 hertz.
And then they hit the continuous latent bottleneck itself, which compresses the temporal resolution by another factor of 4.
So we go from 50 hertz down to that extreme 12.5 hertz.
Right, exactly. And at that point, the audio is represented as a 128-dimensional diagonal Gaussian latent.
And just structurally, assuming a diagonal covariance matrix basically means they were treating those 128 latent features as independent distributions, right? It simplifies the parameterization.
Yeah, it keeps things tractable. And the end result of all this is that a 30-second audio clip maps to a mere 375 latent frames.
Wow.
Yeah, think about that. In a 75 hertz model, that exact same 30-second clip would require over 2,200 frames.
Okay, I have to throw a flag on the play here, though. Because from a pure signal processing standpoint, if you compress a 24 kilohertz audio signal by 1920x down to 12.5 hertz, well, a standard convolutional network should output a blurry, artifact-heavy mess on the other side.
Oh, absolutely it should.
Because convolutions are myopic, right? They only look at a tiny local window. They really cannot preserve complex, wide-band harmonic structures through a bottleneck that is incredibly tight.
You are totally right. A purely convolutional network absolutely would output a blurry mess. But the Qwen team bypassed that limitation by strategically placing window transformers immediately before and after that tightest bottleneck.
Ah, okay. So they are bringing in transformers for the heavy lifting.
Yeah, and these are really heavy computational blocks. We are talking 8 layers, a hidden dimension of 1024, and 16 attention heads.
So they're injecting global long-range context right at the exact point where the convolutions would otherwise just drop the ball.
Exactly. And the placement is the genius part here. They run these heavy transformer blocks entirely at the lowest possible frame rate, which is that 12.5 hertz.
Oh, that makes so much sense.
Yeah.
By isolating the heaviest compute modules to the shortest possible sequence length, they prevent the high-resolution layers of the encoder from getting congested.
Right. You get all the necessary modeling capacity you need without torpedoing your encoding latency.
So smart. And then, to decode that highly compressed state back up to 24 kilohertz, they utilize an asymmetric decoder, right?
Yeah, the decoder is intentionally built much heavier than the encoder. They use 3 residual units per block instead of just 1.
And that asymmetry works because the decoder operates offline, or, well, at least outside the critical path of latent extraction during the DIT training loop. You can afford for it to be heavy.
Exactly. You only decode when you want to actually listen to the output. But, clever architecture doesn't automatically restore high frequencies. The training objectives and the discriminator bank are doing a massive amount of heavy lifting here.
Because they have to resurrect those fine acoustic details from that tiny 12.5 hertz bottleneck.
Right, and standard L1 spectral losses alone just won't cut it. They heavily oversmooth the waveform.
Yeah, you get that classic result where the audio sounds muffled, almost like you're listening to it underwater.
Exactly. So to combat that, the team deployed a really multi-layered bank of adversarial discriminators. You have a multi-period discriminator, which focuses on pitch and voicing.
Which is obviously crucial for human speech.
Right. Then you have a multi-resolution STF key discriminator policing the high-frequency fidelity. There's a multi-scale STFT to ensure transients, like drum hits, stay sharp. And crucially, there's a sub-band CQT discriminator.
Okay. Unpacking that sub-band CQT discriminator is vital because it solves a fundamental flaw in standard STFTs.
Yeah, the linear bin problem.
Exactly. An STFT uses linear frequency bins. The problem is that human hearing, and especially musical harmony, they operate logarithmically. With linear bins, your low notes just get lumped together, and then your high notes get an unnecessary amount of resolution.
Which is terrible for music.
Right. So the CQT, or constant Q transform, uses logarithmic frequency bins. It maps perfectly to musical pitch, kind of like the keys on a piano.
Which is such a great analogy, yeah.
And that allows the discriminator to enforce strict tonal and harmonic accuracy, sharpening those musical transients that a standard STFT would simply blur together.
So they stabilize all of those discriminators using a feature matching term. It basically functions like a perceptual loss in the discriminator's hidden space. But honestly, the most revealing hyperparameter choice they made was setting the KL divergence weight.
Oh yeah, the KL weight. What did they set it to?
They set it to an almost microscopic 10 to the negative 6.
Wow. Okay, let's try to visualize what the KL divergence penalty actually does for you guys listening.
Yeah.
Imagine you were trying to pack different colored sands which represent your audio features, into these perfectly round spherical molds.
Okay, I like where this is going.
So that mold is the standard Gaussian prior. If you have a high KL weight, you are basically forcing the algorithm to pack the sand so tightly that it forms these perfect smooth spheres. You lose all the jagged edges and unique clusters.
Right. And the assumption in classical autoencoders is that a neat, perfectly spherical latent space is desirable. You want it smooth.
But the Qwen team ran an ablation study on this, didn't they?
They did. They bumped that KL weight up to a more standard 10 to the -3.
Right.
And doing so actually severely degraded the downstream text-to-audio generation.
Really? How bad was the drop?
Well, using the exact same diffusion setup, the CLAP score on the audio caps dataset fell from 0.33 down to 0.30.
Because diffusion transformers actually need those jagged edges. Real-world audio data isn't perfectly Gaussian. It clusters in these weird, messy ways.
Exactly. It has texture.
Right. And if you force the latent space to be a smooth sphere, you basically destroy the structural guideposts that the downstream diffusion model is relying on to learn the data manifold. By keeping the KL weight at 10 to the -6, they intentionally left the latent space messy.
It just proves that optimizing an autoencoder for pure reconstruction is insufficient now. You actually have to optimize the latent space for generative learnability. As you said, the diffusion model needs texture to latch onto.
So we have a compact 12.5 hertz representation, and we've preserved all this great acoustic texture. But we still have to satisfy the third leg of that impossible triangle, which is high throughput encoding.
Right, steep.
Because if you are doing online latent extraction, you cannot have your massive GPU cluster sitting idle waiting for the autoencoder to just spit out frames.
And initially, their encoder was way too slow. Running a batch of 64 clips, 30 seconds each, it took 1957 milliseconds.
That's nearly 2 seconds just to extract latents. That is a massive system bottleneck for a training loop.
It is. So to trim the fat, they implemented 3 latency-aware pruning techniques, and they dropped that time down to a blistering 541 milliseconds.
Okay, let's walk through those 3 techniques because they are interesting. Step 1 was stride reallocation. So they shifted the downsampling strides so that the bulk of the parameters operate on lower resolution intermediate features.
Which is just smart resource management.
Yeah, exactly. Step 2 was pruning the residual units. They stripped the encoder down to just 1 dilation, 1 unit per block. And then step 3 was reducing the channel width of the very first layer in the encoder, shrinking it from 64 channels down to 24.
And that third step is usually the one that raises eyebrows.
Oh, it definitely raises mine. I mean, if you are hacking off channel capacity to save compute time, why stop at layer 1? Why not just shrink the channels across the entire encoder and make it even faster?
It's a fair question, but the paper's profiling data provides a really stark warning against doing exactly that. It all comes down to temporal resolution.
Right, because of where that layer sits in the stack.
Exactly. That first layer processes the raw 24 kilohertz waveform, so it is analyzing 24,000 steps per second. Out of the total encoding time, computing features on that first layer alone costs 305.8 milliseconds.
Okay.
Yeah, it is disproportionately expensive compared to, say, layer 5, which might only be processing 50 steps a second.
Right, the compute cost scales directly with the resolution. So cutting channels at layer 1 saves you millions of floating point operations, but cutting them at layer 5 barely saves pennies.
Exactly. And furthermore, when they actually tried shrinking the channels uniformly across all layers, the model suffered a catastrophic collapse in reconstruction quality.
Oh, really? What happened?
The SI-SDR metric, which is the scale invariant signal-to-distortion ratio, it plummeted from a respectable 8.34 down to -2.80.
Oh, wow. I think we should emphasize how disastrous a negative SDR score actually is for the listeners.
Please do.
A negative score literally means the distortion is louder than the actual audio signal. The model isn't just degrading the audio, it is literally outputting pure garbage.
It's completely broken at that point.
Yeah, because those deeper layers, running at lower resolutions, desperately need that channel capacity to model the complexity of the highly compressed signal. By targeting only the highest resolution first layer, they achieve these massive compute savings without destroying the representational capacity of the network.
Right. But, having a surgically optimized architecture like this requires an equally robust data set to force the model to actually generalize. And the training corpus here is massive. We are talking 5 million total hours.
That is a lot of audio.
It is. They utilized 3 million hours of speech, 1.3 million hours of music, and 800,000 hours of general sound effects.
You know, that domain mixture actually creates a really interesting tension for the continuous latent space. Because if you only feed it speech, the model becomes incredibly good at tracking pitch and prosody, but it completely loses the ability to render the wideband frequencies of, say, a full orchestra.
Right. It overfits to the vocal range.
Exactly. But then if you only feed it music, it blurs the sudden chaotic transients of sound effects.
Yeah.
You know, like a glass shattering or a car door slamming.
Yeah.
You really have to force the continuous latent to balance narrowband pitch tracking with wideband transient sharpness.
And curating that 5 million hour data set required some really aggressive filtering for sample rate mismatches and content leaks. You simply cannot have vocals accidentally slipping into the instrumental music data set, or the model learns incorrect priors.
That makes sense.
But honestly, at the 5 million hour scale, the hardest engineering hurdle usually isn't even the math, it's the file system.
Oh, yeah. The classic IO bottleneck.
Always.
Because 5 million hours of audio means millions of small, individual files just sitting on a network drive. When your data loader attempts random access across a network file system to grab tiny chunks of audio, the overhead of network packets and disk seeking completely destroys your throughput.
It's the worst case scenario for a hard drive.
It really is. Your wildly expensive L20 GPUs end up just idling, totally starved for data, while the hard drives are physically spinning trying to find the files.
So to solve that I/O bottleneck, they packaged the curated audio into binary tar shards, and they utilized a web dataset style indexing system.
Okay, so how does that speed things up?
Well, instead of the data loader requesting millions of small files, it reads massive sequential tar files. The index stores the metadata, sample rate, duration, and the exact byte offset alongside the samples.
Oh, okay, so the loader just seeks directly to a specific byte offset in memory and pulls the audio instantly.
Exactly.
I mean, eliminating random small file I/O in favor of large sequential reads is a system engineering fundamental. But the impact here is staggering. They reported an 18% boost in overall training throughput simply from this data packaging solution.
That is huge.
Yeah. On a 5 million hour training run, an 18% speed up saves an absolute eternity of compute time and cluster costs.
So we have a fast encoder, we have a robust data set flowing efficiently from disk, and an architecture that really balances capacity. The ultimate test is how this autoencoder performs when it's actually used as the foundational backbone for training a downstream text-to-audio model.
And the paper establishes a very clear Pareto frontier here. They benchmarked Qwen-Audio-VAE on LibreSpeech for clean speech, audio caps for general sound, and song describer for music.
And how did it hold up?
Well, across every single domain, it outperforms competing low frame rate models like Stable Audio Open, which operates at 20 Hz. Qwen-Audio-VAE secures a lower MEL distance, superior MRS-TFT scores, and better perceptual scores like PSQ, despite running at a much lower 12.5 Hz.
But there is a crucial ablation in the paper regarding that frame rate that we need to talk about, because they actually built a 50 Hz variant of Qwen-Audio-VAE to test.
Okay, and how did that one do?
In a vacuum, that 50 Hz variant actually achieves better raw reconstruction scores than the 12.5 Hz model.
Wait, really? Which naturally invites the question, right?
Yeah.
If the 50 Hz model sounds mathematically better, why did they handicap themselves by choosing the 12.5 Hz version as the final model?
It circles right back to that big O of L squared constraint of diffusion transformers we talked about earlier. A 50 Hz latent quadruples your sequence length compared to 12.5 Hz.
Oh, right, because attention compute scales quadratically.
Exactly. An L of 4x means your self-attention mechanism is suddenly 16 times more computationally expensive. So that slight bump in raw reconstruction fidelity would render downstream generative training just prohibitively slow.
Got it. So the 12.5 Hz bottleneck really is the optimal Pareto frontier. It retains just enough acoustic texture while keeping the sequence length short enough to allow for massive downstream scaling.
And the final text-audio integration results prove it. By leveraging their highly optimized 541 millisecond encoder, they eliminated the bottleneck of latent extraction entirely.
Which freed them up to scale other things, right?
Exactly. This allowed them to increase their batch size by a factor of 4, jumping from 16 all the way to 64 on their 32-node L20 GPU cluster.
Because they could process 4 times the amount of audio per step within the exact same wall clock time.
Yep. So the downstream generator learned far more efficiently. In an identical 36-hour training window, the audio cap's CLFP score surged from 0.29 up to 0.33.
Man, that CLAP score increase validates the entire premise of the paper. An autoencoder isn't merely a compression algorithm, right? It is a system-level enabler.
It really is.
The core triumph of the Qwen team is proving that with surgical capacity allocation, restricting the heavy window transformers to the lowest temporal resolution, relying on asymmetric decoders, and selectively pruning the high-resolution layers of the encoder, you can achieve extreme compression without losing the wideband detail of complex audio.
It forces a paradigm shift, I think, in how the industry evaluates continuous VAEs. We really can no longer judge them in isolation based purely on their reconstruction loss.
Right.
We have to evaluate them holistically based on their compression rate, their encoding throughput, and how their latent space impacts the learnability of downstream generative models.
That actually brings up a final provocative thought to leave you guys with. We spent time unpacking how dropping the KL divergence weight to 10 to the negative 6 improved the generative learnability of the DIT, right? By leaving the latent space messy and clustered, rather than forcing it into a perfect Gaussian sphere.
Yeah, that was a huge takeaway. And the implications of that discovery extend far beyond just audio generation.
Exactly. If perfectly regularized, mathematically neat latents are actively hindering diffusion transformers in audio spaces, do we need to completely rethink how strict we are with latent regularization across other modalities?
That's a great question.
Right. Like when building autoencoders for video generation or complex 3D object generation, are we artificially handicapping our foundation models by forcing the data into perfectly smooth distributions? Sometimes the downstream model just needs the jagged edges to find its way. Well, thanks for joining us for this deep dive into the Qwen-Audio-VAE report. Keep building, and we'll see you on the next deep dive here on AI Paper Slop.